Right, this is section 21 vectors of the C4 booklet. So, bear in mind this is a video, so if you're taking notes in the booklet, please make sure that you pause the video at certain times to make sure that you have time to do it. So I'm not going to pause like I would in a lesson. You need to pause the video and make sure you write things down before we go on to the next example. So this is section 21, vectors of C4, on page 52 of the notes. Now, we're dealing with vectors. If you've done mechanics before, a lot of this will be very familiar to you. So we've got the vector from P to Q. The vector is written with PQ next to each other and an arrow at the top to indicate direction. Now the magnitude of a vector PQ is written with vertical lines either side of the vector. So vertical lines either side means the magnitude of that vector. Now two vectors are equal, so we've got here PQ as a vector which is equal to the vector RS, and the two vectors are equal if and only if they have the same magnitude and the same direction. So they have to point in the same direction and have the same magnitude. They don't have to be on top of each other, they could be in different starting positions, but they do have to have the same length, magnitude and the same direction. They have to be parallel to each other. Now the magnitude of vector is never negative in that sense, but it can be zero, which gives rise to the zero or null vector, and the zero vector is particularly important in mechanics. Right, adding vectors, we call it the triangle law of addition. So if I want the vector O to B, then I can go there directly, that's O to B, but if I go via another point, A say, we would make it equal to OA plus AB. So as long as you start and you finish in the same positions, then the vectors are equal. Now, also important, if you've got the vector O to A and then you try and do the opposite vector going from A to O, then A to O is considered to be minus O to A. So because the minus doesn't affect the magnitude, because you can't have negative magnitude, it affects the direction. So minus means you go in the opposite direction. Now, parallel vectors are vectors which are the same direction. They could have the same magnitude, but they most often have different magnitudes. In that case, we would say that RS was some constant lambda times RS. And if you haven't come across lambda before, phonetic spelling would be L-A-M-D-A, lambda. So that, in this case, RS will be lambda times the vector PQ. So it would be some multiple of that vector. So they would be parallel. Now that's one type of the vector notation. Another type of the vector notation is going to be demonstrated here. So often O to A is often written A underlined. So we underline to demonstrate that it's a vector rather than an unknown constant. Very often when it's typed, you would use the bold format instead. So in this case, I've got my vector A, I've got my vector B, I'm going to call A to B C. Then the same triangular law from before gives us that B is equal to A plus C. Similarly, if you've got OA as the vector A, then A to O is equal to minus A. Right, so unit vectors. Some of you will, if you have done mechanics before, will have come across unit vectors before. So unit vector is a vector that has magnitude 1. Now there are special unit vectors that correspond to Cartesian components. So we've got the unit vector in the direction of the x-axis is called I. The unit vector in the direction of the y-axis is called j, and the unit vector in the direction of the z-axis is called k. So if you've done mechanics before, you'll have done I and j, because we generally work in 2 dimensions in mechanics. If you're working in C4 though, your chances are we're going to be working in 3 dimensions. So we go on to what's called the z-axis, and that's k. Now to get the picture of this, if you've got your x and y axis, you can think of it as this sheet of paper being flat, and then the z-axis points out of the sheet of paper, coming into a third direction, giving us 3-dimensional space. So xi plus yj plus zk can be represented as a column vector x, y, z. If we're trying to find the magnitude, it becomes a case of 3D Pythagoras. So if I've got a cuboid here, what I want really is the length of the vector all the way, because I'm going to make xi is the length of my first side. Then I've got yj corresponding to my width, and then my height will be zk. So if I get the length of the vector that takes me all the way, then instead I have the magnitude of that whole vector. So it corresponds to the length of that diagonal. Now we have to do this in 2 stages. So 3-dimensional Pythagoras. So first we find this length here. So I'm going to call the main one M, I'm going to call this one D, just to make things simpler. So for the magnitude D, for the bottom diagonal, just dealing with the 2-dimensional plane, I get D squared equals x squared plus y squared. Now if I look at M, I've got a second, because that was a right angle. That's a right angle as well, pointing out of the sheet of paper, going back to my previous analogy. So I have a side D going across to there, a side of magnitude Z going up to there. I want the length M, so M squared equals D squared plus Z squared. But going back to the green working, D squared is equal to x squared plus y squared. So M squared is equal to x squared plus y squared plus z squared. And because we actually want M and not M squared, we square root it to get the magnitude. So we get the square root of x squared plus y squared plus z squared. So what we have, as I've said before, is a 3D Pythagoras. Now you don't need to know the reasoning behind this formula that I've just done there, but you do need to remember that. And as I say, it's not difficult to remember, because when we've done the magnitude of 2D vectors, we've just done the 2-dimensional Pythagoras. 3D dimension just goes on in a predictable fashion. Right, so some examples. So find the distance between the points 1, minus 2, 1 and 3, 1, 6. So here, to find the distance between them, first of all we find out what's called the displacement vector is, the vector that takes us from one point to the other point. So we can write that in column vector form. So in the x-coordinate we go from 1 to 3, so we're adding 2. In the y-coordinate we're going from minus 2 to 1, so we're adding 3. And in the z-coordinate we're going from 1 to 6, so we're adding 5. So the vector we add is 2, 3, 5. We then, the distance is equal to the magnitude of that vector. So again, just like the last section, it is the 3D Pythagoras. So the square root of 2 squared plus 3 squared plus 5 squared. Getting out my calculator. I get the square root of 38. Because this is pure, we tend to prefer exact answers to decimals. Example 2. Same sort of idea, but this time we know what the distance is and we need to work backwards to find a missing value. Again, we're going to need the displacement. So the vector that we add to go from one vector to the other vector. So from x coordinate from 5 to 4, we take 1. For the y, we're going from 0 to 2, so we're adding 2. And for the z coordinates, we're going from 3 to k. Now when you've got the algebra there, if we take 3 away, so minus 3, we go back to 0. And then if we add k, we go to k. So that gives us our vector. So minus 1, 2, minus 3 plus k. Now we're told the magnitude of this vector is equal to 3. And we apply the formula like we did before, but now we've got a bit of algebra in it. So the square root of minus 1 all squared plus 2 squared plus minus 3 plus k all squared is equal to 3. Now to solve this, the square root is in the way, so we can get rid of the square root by squaring both sides. We can calculate a bit this as well. So minus 1 all squared plus 2 squared is 5. And we can multiply out the bracket. We get k squared minus 6k plus 9. Squaring both sides will get rid of the square roots. Squaring 3 will give us 9. Take 9 off both sides, we get a quadratic. So k squared minus 6k plus 5 is equal to 0. We need to factorise. So two values are multiplied to give plus 5, add to give minus 6. We get minus 1 and minus 5. And then solving the bit, k minus 1 equals 0 would give us k equals 1, or k minus 5 equals 0 would give us a solution of k equals 5. We were expecting to get more than one value. The question said values in it, so that was a key word. If a question asks you for values in an exam, it's not a trick, you are expecting to get more than one value. Right, next example. Find a unit vector in the direction 3i minus 4j. Now, the first thing we need to do is to find out how big our original vector is. So what its magnitude is. So the magnitude of 3i minus 4j, again, we're using Pythagoras, it's 2 dimensions we're working in here. So it's the square root of 3 squared plus 4 squared. You may have already recognised that this is a 3, 4, 5 triangle. So it's equal to 5. Doesn't matter if you don't notice, you do the calculation, it'll give you the correct answer. You may have also noticed I just wrote 4 and not minus 4. That's because minus 4 all squared and 4 squared are the same. So very often when doing the magnitude, I'll skip any minuses and just treat it as a positive number. Now, so the 3i minus 4j has magnitude 5. We want a vector that's parallel, so a unit vector, which will be parallel, magnitude 1. So to go from magnitude 5 to magnitude 1, we would divide by 5, and that's what we need to do to the vector. And we can just divide the components by 5. And then that vector there is our answer. It's a unit vector, has magnitude 1, it will be going in the same direction. And we're ready for example 4. Which is our final example. So in this case, given two vectors, O to P is 2i plus j minus 6k, and O to Q is 3i minus 4j minus 2k. And we're first of all to find the vector P to Q. So in these sort of questions, what we're trying to find is a route that takes us from P to Q using the vectors we've got. So at this point, we've only got 3 points, O, P, and Q. So if we started at P, we'll have to go to O first. And then we go from O to Q. Now we've got a vector OP and OQ, so OQ is fine, we've got that one. PO, as used in the rules before, is the same as minus O to P. So minus, putting the vector in, 2i plus j minus 6k plus O to Q, 3i minus 4j minus 2k. Then multiply the brackets, minus 2i minus j plus 6k and then once it's nicely multiplied out we can collect the like terms. So 3i take away 2i is I, minus j minus 4j is minus 5j, and 6k minus 2k is plus 4k. And then B, same sort of idea, we're going from O to M, where M is the midpoint of P to Q. So O to M is equal to O to P plus a half P to Q. So we can't really do B once we know what the vector P to Q is. We've got both of those vectors, so O to P, 2i plus j minus 6k plus a half times P to Q from our last question, so I minus 5j plus 4k. As last time, multiply out the brackets, so half I minus 5 over 2j plus 2k, and then we collect our like terms. So 2i plus a half is 2.5 or 5 over 2i. 1j minus 5 over 2j will give us minus 1.5 or minus 3 over 2j. and minus 6k plus 2k gives us minus 4k. And that gives us our answer to example 4. Now this so far is the background to the vectors topic, so we'll be moving on after this to work on new concepts such as scalar product and the vector equation of a line. But before we can really deal with these, you need to make sure you've got these basic concepts down.